Hi, in the previous module we introduced the General Linear Model, or GLM approach towards analyzing fMRI data. In this module we'll talk about how we can estimate the parameters of the GLM. So recall that the standard GLM model can be written in the following format. We have y is equal to x beta plus epsilon, where epsilon is normally distributed with mean 0 and variance covariance matrix V. Here y represents the fMRI data from a single voxel strung out over time. So here we're assuming that we have little n time points, and so y1 is the voxel measurement at time 1, y2 at time 2, etc. all the way up to yn. X is the design matrix, and this contains all our information about the design of the experiment and about which signals we believe are present in the fMRI data. Beta are the regression coefficients, and so those are the unknowns in the model, and they weigh the columns of the design matrix. We want to estimate the beta. And here the epsilon are the noise coefficients, and so here V is the covariance matrix whose format depends ultimately on the noise model that we use, and we'll talk more about this in the later modules. For now, for simplicity, assume that the model y is equal to x beta plus epsilon, and I will assume that the epsilon are IID normal. That means that they're independent, identically distributed normal random variables. So we write this as epsilon is distributed as normal with mean 0 and variance covariance matrix I sigma squared, where I represents the identity matrix. So here the only unknown parameter is sigma squared, and so we want to estimate this. Now the matrices x and y are assumed to be known. Y is simply the data that we observed, and x is the design matrix which we have the ability to specify and where we put in all our information about what we believe is present in the signal. In this model we assume the noise is uncorrelated. And our goal is to find the values of beta that minimize the following quantity. And this is called the least squares criterion. To gain a little bit of intuition about this, let's go back and look at a special case of the GLM, which is simple linear regression. Here let's assume that we have two different variables. We have y, which is the response variable, and x is the explanatory variable. We can make a scatter plot in the following format, and so here for simplicity we're just assuming that we have 3 data points. So this is a special case of the GLM. What we want to find is we want to find a line that best fits this cloud of data. Of course there's many lines that we could possibly use, but according to the least squares criteria, the optimal one is the one that makes the distance between the points and the line, the squared distance between them, as small as possible. So basically what we want to do is we want to calculate E1, E2, and E3 here. We want to square them and then sum them up, and that gives us a score for this line. Now we can calculate a similar score for any possible line, and the least squares criteria says, well, you should choose the one that makes this score as small as possible. Now this can be extended to multiple dimensions. Here's a multiple regression problem where we have y as the response and x1 and x2 are 2 explanatory variables. Now the data are points that are floating in this 3-dimensional space, and what we want to do is we want to find a linear plane that best describes this cloud of data. So here's one potential 2-dimensional plane that we could use, and so again we could calculate E1, E2, and E3. We could square them and sum them up and we get a score for this plane. Then we can rotate it around until we find the best fitting line. So this is basically 2 special cases of the GLM model, and this is basically what we want to do with the least squares criteria. We want to find the hyperplane like this that best fits the cloud of points that we have. So we can write the least squares criterion in the following format, and what we want to do is we want to minimize this quantity q. So how do we do that? Well, we can take the derivative with respect to beta and set it equal to 0. And if we do this in a little bit of algebra, this gives us the normal equations, which can be written as x transpose x beta hat equal to x transpose y. Now what we want to do is we want to get this beta hat by itself. So what we do is we pre-multiply both sides of this by x transpose x inverse, and that gives us the least squares estimators. So the least squares estimators is beta hat equal to x transpose x inverse x transpose y. So in the continuation we're going to call this guy the ordinary least square, or OLS solution. This is the solution, the least squares estimate for the case where the variance covariance matrix is equal to the identity times sigma squared. When we have a more general variance covariance matrix, then we're going to call it the generalized least squares solution, so we'll return to that later. The OLS solution has a number of interesting properties. First, it's also the maximum likelihood estimate, so if we were to maximize the likelihood, we would get the same estimate. It's also an unbiased estimate, so that means in expectation beta hat is equal to beta. So basically, on average, we're going to get the true value of beta by using this estimate, and that's a desirable property. Also, we have that the variance of beta hat is equal to sigma squared times x transpose x inverse. So we know all this information about the OLS solution. One question that we could ask is, well, is it possible to find another estimate of beta, say beta tilde, that has a smaller variance? So can we do better than this estimate? Well, the Gauss-Markov theorem says that we can't. So the Gauss-Markov theorem states that any other unbiased estimate of beta, so any other estimate of beta that has this property of being unbiased, will have a larger variance than the OLS solution. So to illustrate, let's assume that beta tilde is an unbiased estimator of beta, same as beta hat. Well, then according to the Gauss-Markov theorem, the variance of beta tilde, it has to be as big or bigger than the variance of beta hat. So basically what we're saying is, among the class of all unbiased estimates of beta, we can't really do better than beta hat in terms of variance. And so basically we get an unbiased estimate with as small as variance as possible. So that's why we like the OLS solution. And so we say that beta hat is the best linear unbiased estimator, or the BLEU, of beta. So basically, if epsilon is IID, then the ordinary least squares or OLS estimate is optimal. So we have the following model: y is equal to x beta plus epsilon. Then the optimal estimate, the BLEU, is this value of beta hat. However, if the variance of epsilon is equal to v times sigma squared, where v is not equal to the identity matrix, well then the OLS estimate is not optimal anymore. Well then what we have something called the generalized least squares estimate, or the GLS estimate. That is optimal. So in this case, the optimal estimate is very similar. You see that beta hat is equal to x transpose v inverse x inverse x transpose v inverse y. And so this gives us the best linear unbiased estimator for the case where v is not equal to the identity. You will notice here that if we assume that v is equal to the identity, the GLS solution becomes the OLS solution. So the GLS is the generalized form of the OLS. So in summary, here's what we have. Our model that we're going to be using for the next couple of modules is y is equal to x beta plus epsilon. We have the GLS solution, which is the best linear unbiased estimate, that's given by the following format. Now the fitted values, so that correspond to, say, the line in the simple linear regression, or the plane in the multiple regression, is y hat is equal to x beta hat. Now, after computing the fitted values, we can compute the residuals. So the residuals is the distance from the line of the plane to the data points. And so that's simply equal to lowercase r is equal to y minus y hat. And by putting in the value of y hat, x beta hat, and also the estimate of beta hat, we can rewrite it in the following format. This can be re-expressed as uppercase R times y. So the residuals are equal to uppercase R times y, where uppercase R is often called the residual inducing matrix. So even if we assume that epsilon is IID, we still need to estimate the residual variance sigma squared, because remember we said that the variance was the identity times sigma squared, so we still need to know what sigma squared is, so it's the scaling of the variance. So our estimate is going to be equal to the squared residuals divided by the trace of the residual inducing matrix times the variance covariance matrix. So for simple OLS, this is simply the sum of the squared residuals divided by n minus p. For the case where v is not equal to the identity, things become more difficult, and we'll return to this in a later module. Okay, so that's the end of this module. Here we talked about the general linear model and how we can estimate the parameters of the GLM. In coming modules, we'll talk about model building, how we can get the most out of the GLM model, and then we'll talk about inference a bit. Okay? I'll see you then.